My name is Chris, and I'm here to get you started on Project 4. So in this video, I will be introducing everything you need to know about inode.c, which is kind of the core part that I modify in Project 4. As a quick overview, we'll explain first what is an inode and what does each structure in the file system and file.c represent. And number two, I'm going to walk through on how does one use the structure to create and open files in the file system. And number three, I'm going to do another quick overview on how does one access the inode for reads and writes. Number four, I'll do a quick summary of the task you do for index files. And number five, I'll actually do a small example on how you should navigate index files in the file system. Let's get started. So let's talk about inode and inode disk. Initially, it might be pretty confusing on what all these new structures mean because, well, you have file, you have inode, you have inode disk, and they will look the same, what's going on, right? So therefore, we formally introduce them here. So what is an inode and how is it different from files in PintOS? Inode is a data structure that represents a file in the file system. But unlike the file structure you have used in user program, it is a singleton instance. So what I mean is whenever you open a file structure, either in the same process or a different process, that file is associated with this particular singleton instance. So for example, when you open multiple files in the same process, every file may have a different, like how much you have read, etc. But they all share this particular inode, which represents what the file actually is in the file system. So this way you can both have the file and have independent control in each different process. So inode is that singleton instance. So let's look at the internals of an inode. An inode has several fields, but well, the first one is self-explanatory. It's simply the inodes are stored in a global list, and we have a list element. The second part, the sector field, is where the inode is stored in the file system disk. This is important. We'll get back to it soon on what sectors are. Open count is, well, the number of file structures that open this inode, right? This is relevant for removal since when file remove is called, we should only remove a file when everyone is done with it, i.e. we close them or everybody has exited. And that usually means closing them as well. And removed is self-explanatory, whether the file remove is being called on as inode, and until open count has been set back to 0, we can check this field to check if we should remove it. And you're also familiar with deny write count as well, similar to open count. Only when no one else is denying write, we'll allow someone to write. Now, the last field is important. The reason why it's called data is that the structure inode disk is a structure that is supposed to be an in-memory copy of the actual content of the inode on the disk, which we talked about before is stored on the sector here. So a sector represents a piece of storage in the file system, and data here is stored in that small piece of storage. So let's take a look on what inode disk actually looks like in the file system, or now they're kind of equivalent. Is inode is one in the memory, and inode disk is what it should look like in the file system, but let's keep going here. So each inode disk structure is exactly block sector size long, right? Or 512 bytes in PintOS. This is because disk allocates storage, well, conceptually similar to virtual memory pages in blocks of consecutive spaces, and you know what are the benefits of paging, right? We assume an inode can be stored entirely inside a block. This might not always be true, but here we're just meaning that the I/O disk should be an exact copy of 512 bytes in the file system, right? We're assuming it can be stored within 512 bytes. I'll explain the fields of the I/O disk with a visual representation. So here's a visual representation of the structures. Let's suppose inode is stored in, let's say, sector 2. So 0, 1, 2 were stored in this, well, sector 2, but it's the third sector. It's the third 512 byte sector in the file system disk, right? This means its content, inode disk data is stored in the sector 2 of the disk, and when you copy this piece of data, it should be the same. Well, yeah, it should be exactly the same unless you change one or the other, which we'll talk about as well. So now, the first field is start. Start means kind of the start of the file, like the actual content of the file now. So now let's suppose the start sector is 12. This means that the file starts from this sector block. And if the length of the file is 1024 bytes, which will span two 512 byte blocks, will occupy both the sector 12 and sector 13. So in this case, we have a file that's consecutive in the file system, right? 12 and 13 are consecutive to each other. Now that you know how each part of the I/O works, let's walk through inode create. So I chose this function as it teaches a few key lessons for inode and file system manipulations. So first, it teaches you how to, allocate disk space, right? You will need this often in Project 4. And second, it teaches you how to write data to the disk, which we'll do like when you start implementing stuff, you have to change the file system at some point. And it teaches you how to also use each part of the inode disk, right? This will put our previously introduced concepts to use. And number 4, it tells something very subtle but important, right? Whenever you want to make a change for an in-memory copy, it has to be written back to the disk. Maybe not it's, let's say, not immediately, but whenever it should be before someone else using it, right? Otherwise, you have a race condition because someone else will read the one in the file system, but is different from what you have changed in your memory. Right? This will be especially important later on, where you will extend the inode disk and have indirection metadata. So let's walk through how inodes are created. First, we initialize the inode disk structure. You can see by the callocs here, and we also want to make them look exactly like what is looked at the disk. We initialize its parameters. We initialize the length and the magic. Ignore the magic. You don't really need to know them here. So after initialization, we have to allocate free spaces from the file system disk, which we'll use free map allocate. This function's first argument takes in how many sectors you need. So for example, if you want 2 sectors, you give it 2 here. This will give you a consecutive block, 2 consecutive blocks. And when this function returns, it will change whatever reference is passed here, right? We're passing a reference, so the function can actually change this value. So after the function call S will be the correct sector indexes, let's just say. And also free map, you'll have to release them since if you have done swap using, let's say, a bitmap, you have to release the bits on the bitmap after you say, okay, I don't need this anymore, right? Okay, let's continue. Number 3, we have to write this inode disk to the disk, right? Otherwise, nobody is going to be aware of our file system changes. Right, so here block write takes, if takes the disk inode in the end and writes them into the sector. Right, this is usually how you should use the block functionalities. And in the end, we zero out any data and free the memory spaces we allocated. Right, so that's inode create, and we can subsequently check out inode open. So we have created something. So how do you open something now? So first we have to initialize the inode sector, and somebody has to give us this particular sector that we have to open, which you kind of don't have to worry about at the moment. You'll see how they work. And well, yeah, because I'm using an isolated instance, but someone has to know the sector. You'll no, you'll know this later when you're doing directories. Where in directories, you'll actually search the file system for this particular sector, right? Okay, so you initialize everything. So I know sector is sector and open count, etc. They're the default values. And we'll read back whatever is in the sector created in our previous steps into our inode data. So now you have an in-memory copy of whatever is on the disk for your inode, which you can then use for reading. And talking about reading, there's quite a few things involved. So how do you read and write using an inode? We leverage some basic arithmetic calculations here. So first, we read write. When we read and write, we usually start from the offset. Right? And your read write syscall, you give the syscall an offset, and they're supposed to read from that. But since we're storing things in sectors, we have to calculate, well, which offset does this, let's say, which sector does this offset actually belong to, right? Since we're in factorial blocks, well, which factorial blocks does it belong to? Right? Then you can look at the byte to sector function inside how it exactly works is how you exactly would expect. You divide it by the block sector size, which should be 512 bytes. Then you just get an index that, well, tells you which sector is it, right? And since the file is consecutive, you can just add this index to data.start, which is the sector number, and you're good to go. So then, after you know where the sector is, well, you'll still have to get the correct offset, which you can easily do by just doing a modulo of the block sector size, right? So like, where is it actually in that 512 sector? And afterwards, you'll read the entire sector. So the sector we found, and we're reading them into a buffer. Then you'll just copy from this buffer. Let's say, this here we use bounds plus sector offset, which we calculated back above here, because we don't want to actually read anything. We don't actually want to copy anything, let's say, any like garbage data in there. We only want to copy what's actually useful, starting from the offset. So here's where we do it. Ignore these things as they're situational dependent. I just copy them from file write and read. So don't pay too much attention on them. This just means copy, right? Okay, so now we've known how to read and write. We know how to create and open inodes. Your next task is, well, index files. So why do we actually need index files? So currently, files are stored contiguously in the disk. As you have seen before, we're using simple arithmetic. We just divide by the block sector size and add that index to the start. But contiguous files have drawbacks. You should have learned this in lecture, or we'll also discuss it in tutorial. So we want to store files efficiently, and to do that, we need an indexed file system. So your first task in project 4, hope is your first task, is multi-level index file system. So in here, you'll create some level of indirection. One example is you have some direct blocks, you have indirect blocks, you have some doubly indirect blocks, and you also have some unused data. But you want to keep this whole structure within 512 bytes, so you can use this unused array to fill that up. Right. Okay. That's so given we have some structure like this, I'm going to use a more simpler one using a 5 direct, 1 indirect index files. How do we create, let's say, an indexed inode disk? So, like, be warned, I'm kind of expecting you to know a little bit about file system, index file system from this point. So, if you don't understand, review them, and then it will make more sense, right? So here we have 5 direct, 1 indirect. So first, given we have 5 direct index blocks, we'll need to allocate 3 disk space 5 times. Right? Remind, they should not be required to be contiguous. So this means we'll allocate 1 disk sector at a time. Right? We're assigning it to each direct index block. So we have a direct index block here, which is 5 elements, and we're assigning them to the reference. We're passing the reference to them. So after free map allocate finishes, well, it will go here. The correct sector will go here. Well, if it errors, you can have some error handling with a go-to statement. It's okay in PintOS since we're using a not so complex C program. So you can just make sure you don't have any, you don't misunderstand the go-to statements, right? Use them correctly. But since you have done B58, I'll expect you to be able to do that. Right? So, as we are reminded multiple times, so as reminded multiple times, whenever you change something in the inode disk, you have to write it back. Right? Here, we allocated, let's say, 5 direct blocks. Well, the file system doesn't know that, right? The file system still thinks, okay, I haven't allocated anything. When somebody opens it up and says, okay, you haven't allocated anything, sure, but you've actually allocated a lot of stuff, right? So then you would need to write it back for others to see, well, you have changed something, right? So now, given this example, I would expect you to know how to extend it to an in direction after you've extended the tutorials and kind of read through the project documentation as well. And that piece of code is way too long, so I'm not going to do it here. So another example that I'm going to do is also one of the first things and useful function you should implement after you have set up the inode structure. This is that you should change the byte to sector function, right? Since we have an indirection, we cannot rely on, previously we're assuming a consecutive, contiguous disk space for the files, but now it's not the case, right? The files can go anywhere in the file system. And you also have indirection, which means some, let's say, sectors may store pointers, and how do you navigate them, right? So you need to update the byte to sector function, and this function should give you whatever you give it an offset or position. This function return which sector it belongs to. So I'm going to demonstrate a sample calculation of inode structure with 5 direct and indirect block. So again, just if you don't understand, it's fine because you haven't attended like the index file tutorials, you haven't looked at the relevant lecture slides yet, right? So first, let's look at the direct blocks. It's easy to know which sector a piece of data belongs to if they're in the direct blocks. Right? If it's within the direct block storage space, which here we have 2,560 bytes, 512 times 8, times 5, right? So then just, return which 512 byte sector it is in, right? So we just divide the position by block sector size, and well, whichever one it lies in, we should return that particular direct block. I forgot a retention name here, but it shouldn't matter. So this is assuming that the position we gave to byte to sector is less than 2,560 bytes, because that's kind of all the direct blocks we have. But now what if it's greater? What if it goes to the indirection? So given our position, one position now it's in the indirection, we have to copy over the indirect sector pointers from the file system disk. So first we create this pointer in-memory buffer. Then we read from the disk where the indirect block from the file system using its sector, right? Indirect here should store a sector value, like how you did, which you should have initialized in the inode create, right? So pointer now after the read should have the same block sector content as in the device disk, the file system disk, right? The easy way to think about what pointers are is think of it like a direct, like this a similar array as direct, but now with 128 entries instead. So given that knowledge, we can now calculate which sector in this pointers array do we want. Right, first, I forgot to click. It's just it's mentioning that it's similar to the number of pointers you can store. Like it's similar to direct 5, but it's depends on how many pointers you can store in a block. Well, in this case, we have 4-byte pointers, which because 4 block sectors are 32 bits, right? So if we want to calculate where the position is in which pointer contains that position, we have to first minus 2,560 bytes. But the reason is, well, indirection starts after the direct blocks, right? We minus 2,560 as the indirect only stores data above that region, right? So then, using the similar arithmetic, we retrieve the sector similar to what we did in direct. It's just now we have what is it? How many? Yeah, it's just now we have a block sector size divided by 4, number of blocks, number of sectors. But I didn't do divide by 4 because note, position is still in number of bytes, and each sector stores 512 bytes, so we still have to divide that. It has nothing to do with pointers. Some people get it wrong, but it's a small mistake, right? So here, the pointer stores sectors, and using the position divided by block sector size, you would know, well, which pointer am I in, right? Which of the pointers, which is 512 bytes, am I in? So then after this point, you should realize that, okay, this is just kind of a repeat of what what this first part does, right? What we did in DirectOS is just we have to read something from the disk to get the pointers, and then we do the same calculation. Well, you're kind of right? Because at this point, if you want to extend it to a doubly indirect, you would just perform this in a similar style, but you just need an extra layer of pointers. So don't be afraid, you're correct. This is how you do, and you'll see redundant code from time to time when you do the file system project, right? But be sure follow the similar formats as you did for like project 3, project 2, project 1. Just be modular, make your code easy to read. It'll benefit you the most, us second, when we'll be reviewing our code, but it's not the first priority, right? Be sure your teammates and you can read the code. Okay. So then your next, I'm just going to summarize the relevant tasks for index files. Then you implement file growth, which given an index file, well, file growth is much more feasible. And then the synchronization. Previously, you had to put locks around read write of the file system. Well, now it really doesn't need to be the case because you can synchronize them at the disk device level, right? You will synchronize the file growth, you'll synchronize file reads and file writes, and you should find more information on that in the project for documentation. So all these points will be discussed during tutorials in more detail, and I hope you have a good project 4. Thank you.